All right, super. So thank you very much, Mike, for agreeing to come to give us this talk. Really delighted to have you here. So I've known Mike for my entire professional career. He's done just really important work in many different areas. So some proper subset of those interesting things are working on anisotropic hydrodynamics, viable instabilities, hard thermal loops, and now going into quark-gluon suppression, complex potentials, and various interesting methods in that direction. And I'm really interested to hear what you've got to say, and really looking forward to your talk. So please take it away when you're ready. And I guess maybe one last question. You're happy to have people ask questions as you go along?
Yes, of course.
Super. Thank you so much.
Okay. First, thanks for the invitation. It's an honor to be able to give you guys a couple of presentations. The first one is sort of introductory. I tried to this morning look at what presentations you've had before, so I could not do double coverage, but there's some introductory material here that has to be stated just to make sure everybody's on the same page. Okay. So first, setting the baseline, there's these particles called quarks and gluons. They're part of the standard model, and they make up the constituents of what we classify as the strong force. The quarks exchange gluons and are stuck together with these gluons. Under normal conditions, quarks and gluons are confined inside of a class of particles called hadrons. Hadrons consist of two subclasses: baryons, which consist of 3 quarks or antiquarks, and mesons, which could consist of a quark and an antiquark. Familiar baryons are the proton and the neutron, and then more exotic ones that might contain things like a strange quark are the lambda baryon, or a charm quark, it's the lambda C. And then mesons, you don't hear too much about in popular discussions. They're things like pions. Again, they're a quark and an antiquark stuck together. And there's different varieties of these, like the kaon, which is an up quark and an anti strange quark. Now I put ... in here because there's a whole family, a zoo of baryons and mesons, and it was in the 60s that people started to try to figure out how to understand the proliferation of all of these different baryons and mesons. And the understanding at the time came out from this quark model, in which you can build up all the baryons from 3 quarks and the mesons from a quark and an antiquark. Now, the protons and neutrons themselves are grouped together into the nucleus of an atom. This is not to scale. It's just a cartoon that I found online. And then we have the nucleus of the atom, and then we have electrons that are orbiting around it. One of the features of the theory that governs quarks and gluons, which is called quantum chromodynamics, is that quarks have 3 different color charges. So in addition to having electric charge, which turns out to be 1/3 of the normal electron charge, or minus 1/3 of the normal electron charge, they have another kind of charge, which is called color charge. And hadrons in general are colorless combinations of these color charges. Sorry, there's a very loud noise here. I don't know if you can hear it. Good. So normally we have to combine a red, a green, and a blue quark, and that in this picture down here on the left is how we add up the color charges. If we add up red, green, and blue, we go to the center of this diagram, which is white. That is a colorless or color charge-free state, and that's the normal state of baryons. In a meson, you can combine an anti-color with a color. You can sort of interpret that as well from this little diagram below. An anti-color for red might be this kind of bluish teal color that's sitting here on the top. If I combine this bluish teal color with this one, I also end up with a colorless combination. Now, the reason that typically the quarks and gluons are stuck inside of these hadrons is that they're very strongly interacting. You can think of these as, you know, tiny little springs that are holding the quarks together very strongly. Now, you can then ask a question, is it ever possible to see a quark by itself? And under normal conditions, no, because you always have to find them in these color charge-free combinations. And even if you were to knock one out, some quarks and anti-quarks would be created out of the vacuum that would then balance the color charge, and you would result, the final result of that would be yet another ensemble of hadrons. You would never be able to liberate a quark. But one way that you might imagine liberating the quarks is to take some ensemble of hadrons and put them in a box, and then heat up that box to a super high temperature. And if you did that, eventually the momentum of these hadrons flying around in the box would be large enough that they would be slamming into each other and breaking up all the time. You would generate a kind of plasma of quarks and gluons. And in this cartoon, I only show the quark degrees of freedom. This phase of the matter is analogous to a normal electromagnetic plasma. In an electromagnetic plasma, we rip the electrons off from the nucleus, and we have then a electrically charged plasma where electric charges are allowed to roam freely around. And now in this case, you get color charge allowed to roam around freely inside of this box. Now, if you go back to a region where the temperature is low enough, you'll go back into this hadronic phase of the matter where the interactions between the quarks and the gluons become strong again, and they clump back up into 3s and 2s. Now, this temperature at which this phase transition occurs is quite high. It's 10 to the 12 Kelvin, so on the order of a million times the temperature of our sun. You can estimate this temperature by just saying, well, once the momentum exchange becomes on the order of the pion mass is about 140 MeV. And so once you get to a temperature on the order of the pion mass, something is going to happen. That's the sort of cartoony way of understanding the quark-gluon plasma phase transition. And that's how you arrive at this 10 to the 12 Kelvin number. Now, you can ask, well, why do you care about this? And fundamentally, it's because if you trace back the history of the universe, starting from us here over on the right-hand side of the diagram at, some 13 billion years ago, if you go back in time, as we know, the Big Bang Theory says that the universe got hotter. And if we cross this time of 10 to the minus 5 seconds after the Big Bang, that's when you start to exceed this temperature of 10 to the 12 Kelvin. And it's at that point in time, before 10 to the minus 5 seconds after the Big Bang, that the entire universe was this quark-gluon plasma phase. Now, there were some other components of the standard models, like W bosons and things flying around, but our primary interest is in these strongly interacting particles, the quarks and the gluons. Now, going forward in the history of the universe, once you cross this phase transition time, then that's when you had the formation of hadrons, baryons, and mesons here. And then at a much later time, you started creating the primordial nuclei, and then at a much later time, you created atoms. Now, although so this is, as I've said repeatedly, this is a phase transition. It's very similar to, at least qualitatively, what would happen if I had, water vapor or gas, hot steam. I let it cool down, and then I'm going to go to a phase transition to the liquid phase. And then you can ask the next question: well, why is that phase transition so important for us to understand? And that's because 98% of the visible mass in the universe is made during the quark-gluon plasma phase transition. Now, of course, with the advent of LHC, we discovered the Higgs, and the Higgs is fundamentally responsible for imbuing particles with masses, but it gives particles what are called their bare masses, and it only gives quarks a mass on the order of the MeV scale. So most stuff is made up of up and down quarks, and as you can see from the plot on the lower right, this is in MeV here. They have very low masses. But when you're in this low temperature phase of QCD, what you find is that there's another way to generate mass, and that's not through interactions with the Higgs field, but interactions with something called the quark condensate. And what the lower left-hand plot shows is a plot of the sort of acquired mass of a gluon in this case, as a function of the gluon's momentum. The points on this plot are measurements from something called lattice QCD, and the lines here come from some Schwinger-Dyson-like model of the non-perturbative gluon propagator. And we can see in the low momentum region that we're getting, now this is in GeV, we're getting masses on the order of 300 MeV. So that's a quite large increase in the mass, and that's why we quote this number up here, that 98% of the mass of the universe is the visible mass is created during this quark-gluon plasma phase transition. Now this effect primarily gives large masses to the light quarks. It's less important for the heavy quarks, as you can see from the plot below, because the heavy quarks already have a very large mass to begin with from their interaction with the Higgs field. So this additional mass that you would acquire from the interactions, the QCD interactions, is small. Now, although I told you that you can sort of ballpark the phase transition temperature around 10 to the 12 just by looking at where a temperature on the order of the pion mass, we now have a quite good understanding of the QCD phase diagram. And now I've added another axis. So the vertical axis here is the temperature measured in units of MeV. The horizontal axis is something called the baryochemical potential, also measured in units of MeV. The baryochemical potential is measuring the excess of quarks over antiquarks. In normal nuclear matter that we have in the room here in Canton, I presume also there where you guys are, has more quarks than antiquarks. So you live over in this part of the phase diagram. In the early universe, however, you were living over in this part of the phase diagram where there was approximately the same number of quarks and antiquarks. And if you look in this very high temperature and low baryochemical potential region, you can actually do numerical calculations of the equation of state, and I'll show you some results for this in the next slide. But what you find through these very careful numerical calculations is that there is a phase transition as predicted back in the 80s, and we can now pin down this phase transition to approximately 154 MeV. Now, it shouldn't be surprising that this is on the order of the pion mass, and then there's some wiggle room here. Now, the reason that I put approximately equal to 154 MeV here is because the QCD phase transition, when you have 3 colors and 3 flavors of quarks contributing, turns out to be what's called a crossover phase transition. And what that means in practice is that the order parameter for the phase transition changes continuously as I go from the low temperature phase to the high temperature phase. Now, this is not a feature that's specific to QCD. Even water has a crossover phase transition. If I take water and I heat it up under very high pressure, I can actually make a continuous phase transition between the water and water vapor or gaseous phases, and that's called supercritical heating. Another feature that we see from the water phase diagram is that region of crossover ends in a critical point here. And then we have a solid line drawn in the phase diagram. That's to indicate that there is now a first order phase transition, where if I were to cross water here across from the water to the water vapor phases, there would be a discontinuous change in the order parameter of the theory, and there would be associated latent heat that I would have to inject in addition to make the transition between these two phases. So the same feature exists in the QCD phase diagram. We expect, based on this analogy, that at some point the crossover will end in a critical point. If you're sitting right on this critical point, the order of the phase transition would be second order. That would mean that the order parameter is continuous, but the first derivatives of the order parameter are discontinuous, and then we transition into this first order phase. Now, one of the key questions that we try to address in heavy ion physics is where exactly is this critical endpoint of this line of first order phase transitions? And I guess more generally, does it exist at all? And the way that we're doing this is experimentally. I won't have time to go into that today, but let's flip to this next one. Typically high energy heavy ion collisions, where what we do is we'll take say a lead nucleus and another lead nucleus, accelerate it up to nearly speed of light, slam it together, and then we'll generate a phase of matter that has very high temperature but low baryochemical potential. The reason it has very low baryochemical potential is because at very high energies, QCD, quantum chromodynamics, the theory that governs quarks and gluons, is an asymptotically free theory. So at very, very high energies, the quarks that make up the nuclei, my two lead nuclei, essentially pass through one another, and they carry all the baryon content down the beam pipes going to the left and the right, and the stuff that comes out in the middle basically has zero baryon number. It's mostly gluons. You could ask the follow-up question, why don't since the gluons are also governed by QCD, why don't they just fly through one another? And that has to do with something called the color glass condensate or saturation physics, which you have an expert in the audience there with you, if you can ask about later. And there what you find is that simply the number of gluons is so high, it compensates for the smallness of alpha S. So the number actually goes like 1 over alpha S, and this cancels some factors of alpha S. So the gluons actually do interact significantly. Gluons don't have any baryon number, but you can then at a later time produce quarks, but you always have to produce them in pairs, a quark and an anti-quark. And by definition, a quark has, plus 1/3 baryon number, and the anti-quark has minus 1/3 baryon number. So it's baryon number free. So in the high energy limit, the initial condition for the stuff that you want to model lives up here in nearly zero baryochemical potential and very high temperature. And as we cool the matter down, it's going to move over here in the phase diagram, going down basically along this axis. And if our numerical calculations are correct, it will go through this crossover phase transition. Now, if you wanted to find this critical endpoint, it turns out what you want to do is not go to the highest energy collisions. You want to go to lower energy collisions where there are significant interactions between the quarks, and then the quarks will be stopped, and this is called baryon stopping, and they'll appear, in your detectors that you have finite baryochemical potential. So essentially, you're moving the initial condition from over here in the upper left of the phase diagram to the right. And let's imagine we were sitting right here at this point in the initial condition, and it was cooling down. There's a chance that we might pass through this second order critical endpoint. And then again, this is a completely different talk. There might be some signatures in your observables that you actually pass through this. Now, again, I circle back to the question mark here. We don't know where it is, right? So that's why there's a giant experimental program to try to find it. Different theories predict it's, in different places. The lattice can provide us some constraint, only that it's beyond this sort of point, that I've drawn here. But it could be all the way over here. In fact, there are some models in which it doesn't exist at all, and that you just have a crossover all the way down to here. Good. The other three pieces that I put here on the phase diagram are of interest, in particular to, well, people all over the world, but in particular also to people at Kent State University, because we have people working on high density QCD here, where you're trying to model neutron stars, which are sort of cold neutron stars. They have temperatures on the order of MeVs. Which is very small compared to the Fermi energy of the neutrons there. So we call that a cold phase. But you can also generate hot and dense matter if you look inside of stars that are exploding into supernova, or neutron stars that are merging together. My focus today will be on the high energy collision part of the phase diagram. In particular, I'm going to focus on the highest energy collisions that we've been able to do, which really throw us over into this part of the phase diagram. So the next slide is showing you three things. First, let's define the axes. This is a measurement of what's called the equation of state of the quark-gluon plasma. The vertical axis here is the pressure of a gas of quarks and gluons, or the pressure of QCD more precisely, scaled by the ideal gas limit of the theory, which would be just Stefan-Boltzmann gas with quarks and gluons flying around, not interacting at all. If we go to asymptotically high temperatures, we expect this ratio to approach 1. So we expect to eventually get up to 1 on the vertical axis. But what's shown here is actually the range of temperatures that are probed experimentally. The points in red here with little error bars, those are lattice QCD calculations, in this case from the Wuppertal-Budapest collaboration, going from roughly 120 MeV up to 1 GeV.
Sorry.
And as you can, yeah, go ahead.
Why would we expect it to go to 1? I don't exactly see why that.
Yeah, so why we expect it to go to 1 is because QCD is an asymptotically free theory. As the momentum exchange between the quarks and gluons goes to infinity, the coupling constant goes to 0. And as I heat up a gas, what I'm doing is I'm making the particles move faster and faster, and the average momentum exchange of the particles in the gas goes up. So that's why eventually we expect it to go to 1.
Right. So we don't have any saturation effects that counteracted like we did in the previous steps.
No, we don't.
Okay.
In fact, yeah. So with the next line on the plot is the black line. That's a calculation by myself and collaborators, just based on perturbative QCD. You can just sit down and with lots of work, you can calculate the QCD equation of state. This is a resummed 3-loop order calculation. And as you can see, it seems to describe, at least for temperatures above roughly 200 MeV, the lattice data quite well. At some point, though, it breaks, and that's right around the temperature of the phase transition. We see that, well, this modeling it as a sort of gas of quarks and gluons no longer works, and something else is happening. But we kind of understand what that something else is. It's because the quarks and the gluons are no longer the relevant degrees of freedom, because they're clumping up into hadrons. And it's a hot hadron gas, so it's not just going to be the normal hadrons that you would you imagine, so protons and neutrons and lambdas, but it's also going to be their excited states, because they're slamming into each other quite frequently still. So you have to include also the resonant states. So what you can do in practice is just go to the PDG and then read out every hadron and hadron resonance, and then make a thermodynamics model that's based upon just a gas of massive hadrons and hadron resonances, and that would give you this sort of cartoon orange line that I drew here. Of course, going up in temperature, we see that that also fails to describe the lattice data. That's because, again, we've transitioned into these quarks and gluon degrees of freedom. So the other lines here, the vertical lines, are showing you the sort of initial temperatures that we generate at different experimental facilities, and I'll go into some details about those in a few slides. There's the relativistic heavy ion collider at Brookhaven National Lab that sits off of Long Island to the east of New York City. They collide gold on gold at 200 GeV. There were some runs at LHC at 2.76 TeV. They were originally supposed to run at this collision energy, but because a magnet exploded, they reduced the beam energy out of an abundance of caution. It turned out to be great for us because we got then data at 2 different collision energies, and it allows it to test the models. But as we can see at these highest at RIC, you might wonder, right? Do I have the temperature high enough that I'm clearly in this quark-gluon plasma phase? But once we get to the highest energy LHC collisions, we're clearly in the quark-gluon plasma phase. The next slide is just a bit of advertisement. So what is this black line? Well, the black line comes from this giant analytic expression. So it's amazing that we were able to do this 3-loop calculation. This is now at finite temperature and baryochemical potential. That's this mu symbol hiding here, and it comes from doing some first principles QCD calculation. But it's not perturbation theory in the traditional sense. You have to do a process called resummation. So the propagators in this graph are actually hard thermal loop propagators that have some infinite order Feynman diagram resummation hiding inside of them. And likewise, the vertices in all of these Feynman diagrams are resummed vertices. Now, the reason you have to do all this resummation is because normal perturbation theory does not converge in this phenomenologically relevant range. And it's only after you do these resummations that it actually works. But just as a bit of self-advertisement, this calculation took roughly 17 years to complete, and we were quite pleased when it described the lattice data. And I could show you slide after slide of other lattice data that it works for. But just to another thing, I guess, for students in the audience, even if you think your project is long, this one was longer, and it's important not to give up. Good. So experiments and phenomenology. So I covered this a little bit. So what RIC does at Brookhaven National Labs is they collide, at least at the highest collision energies, gold on gold at 200 GeV per nucleon. This per nucleon is important. Remember, we have on the order of 200 nucleons in a gold nucleus. So you have to multiply this by another factor of 200, and you get some crazy number of measured like 4 TeV or 40 TeV. I don't know if I'm doing the math right. It's a crazy high amount of energy that you're depositing into a rather small volume of space. And this was the initial temperature that I indicated on the previous slide. And then there were these 2 runs at LHC. As I mentioned on the phase diagram slide, RIC has been for the last few years decreasing the beam energy to try to go out into the finite density direction. And there you're probing lower temperatures plus finite baryochemical potential. There are future experiments coming online. Some may be already happening at NICA. I don't keep track of NICA very well. FAIR is still under construction, and they'll collide uranium on uranium at this collision energy in order to once again probe this region of the phase diagram. The animation that's running in the lower left-hand corner was provided by Bjorn Schenke. It's a hydrodynamic simulation of the collision of 2 nuclei. There's some features here to describe. If we see these sort of lumpy pancakes receding from one another, the simulation starts at the moment that the 2 nuclei collide with one another. The picture is done in the lab frame, and because of that, the nuclei will appear Lorentz contracted along their direction of motion, so that's why they look pancake-shaped. And the stuff that's being drawn out here between the two receding nuclei, that is the quark-gluon plasma. Now, the quark-gluon plasma, it lives for roughly 3 times 10 to the minus 23 seconds. That's you measure this in yoctoseconds, which is the smallest subdivision of time that has a name. And the volume that you create, has a transverse extent on the order of 10 to the minus 14 meters. And you're dropping that, tens of TeV sort of energy into that tiny volume. It's not surprising that you can generate a very high energy density phase in between these two receding nuclei. And this colorful thing is just my cartoon indicating that there's some quark-gluon plasma with color charge. Now, after the as this thing is expanding, the quark-gluon plasma is cooling, right? Like any gas, if it expands, it cools down. It's expanding in this longitudinal direction because it's being pulled between the two receding nuclei, but it's also because there's going to be some pressure gradients in this direction, it will also expand in this direction. So it will cool as a function of time, and eventually you'll cool down below this 200 MeV temperature. And it's at that point that the quarks and gluons clump back up into hadrons. And then what the experimentalists observed, so this is an actual visualization of a lead-lead event by the Alice collaboration at 2.76 TeV collisions. And this spaghetti-like mess that you see over here are hadron tracks, right? So they're all the particles that were collected. And if you were to take all of these particles that were collected, put them on a scale and measure the weight, you'll find that it weighs more than the two nuclei that you put in the beginning, right? So we actually generate mass during this collision by converting kinetic energy of these two nuclei into matter. So we actually create matter in the course of these collisions. So a few more details about RHIC. Now, RHIC used to have, it started roughly 2000, so 23 years ago. It used to have 4 functioning experimental stations. Over time, they shut down 3 of them, Phoenix, Phobos, and Brahms, and then there's only the STAR, and STAR was focusing in recent years on this beam energy scan. Phoenix has since undergone a revival and now has risen from the ashes, and now it's called S-Phoenix. I believe the S stands for super, but it's a super Phoenix. So they'll be collecting data for the next 3 years with their focus being on hard probes, things like jets, also quarkonia, which are my interest. So these are the experimental stations that, at least in the original RHIC design, existed. Just a second, I have to let somebody in the door. All right. Now in the quote unquote modern era, we've moved to the LHC. Again, there's 4 experimental stations around the ring. The ring is bigger because we need higher energies, and it's harder to bend particles that are moving closer to the speed of light. All of this is hidden underground, and there's the CMS, LHCb, Atlas, and Alice collaborations, which have their own detectors that have different specialties. So CMS's specialty is muon detection, this compact muon solenoid detector. LHCb's focus is also sort of on mostly on high energy stuff. Their original design wasn't for heavy ion stuff. But neither was CMS. The original heavy ion sort of collaborations were Atlas, and Alice is the one dedicated heavy ion collision experiment. But luckily they didn't find supersymmetry. So now these guys are actively also collecting data for us, and there's large large heavy ion groups within these collaborations now, and that's great because it provides a cross-check on all of the information that's been gathered by the various experimental collaborations. So this is a slide just showing a cartoon picture of the history, the temporal history of a quark-gluon plasma event. I had a left-moving nucleus that was this little pancake. I have a right-moving nucleus, this pancake, and this is a space-time diagram. Time is on the vertical axis, and the longitudinal coordinates on the horizontal axis. At the very first moments after the nuclei pass through one another, that's when you have what's called semi-hard particle production. This is the region of the colored glass condensate and saturation physics. So this red region here is highly occupied gluons and is best described by actually classical Yang-Mills dynamics instead of something like a Boltzmann transport kind of theory. But again, the quark-gluon plasma is expanding. So what happens is the number densities decrease as a function of time. Eventually, you cross into a region where the number of gluons is now below this saturation threshold, and I can start modeling them as little quantum billiard balls bouncing off of one another, and that's when you enter into the sort of what I'll call the transport phase. But you don't immediately generate an equilibrium quark-gluon plasma. That takes some amount of time. Formally, it never happens, but you can say, well, when does it get within 10% of equilibrium? And we can all have a gentleman's or gentlewoman's agreement that that's close enough to equilibrium to call it equilibrium. And that happens at about 3 Fermi over C after the collision. And that's when you would think that sort of viscous kind of hydrodynamics approaches will work very well. We've been surprised in recent years to learn that they actually work quite well also in this orange region. There are ways to improve their agreement in the orange region. That's another talk. Will mention anisotropic hydrodynamics. So as we go forward in time, the thing cools down, and then we have a period of time where it's a hot hadron gas, including the resonances, as I said earlier, and then eventually it's still expanding. Eventually, those hadrons stop interacting with one another strongly, and then you reach a period of kinetic and chemical freeze out, and they just sort of fly to the detectors. Those are the things back here that the experimentalists detect. Did I hear a question? No. Okay.
Noise from outside.
Good. Okay, good. And here in this little part of the cartoon is just showing you what that would look like, if you were sitting in the lab frame very close and you were microscopic and could actually see such a thing. I wouldn't recommend doing that, but if you could, this is what it would look like. And you can see that initially it's just expanding longitudinally, but as I go forward in time, it starts to also expand transversely due to the pressure gradients in the transverse direction. Good. Can somebody tell me the time? How much time?
35.
Sorry? 25?
Yeah.
Oh, okay, good.
33.
Good. Okay, good. Thank you. So some key experimental observables. So how do we observe the quark-gluon plasma? Well, experimentally, we only have access to these hadrons that emerge in the final state. And it's our job as theorists to make predictions about the properties of this large ensemble of hadrons that emerge from the events. The first thing that you might consider is just counting the number of particles. So how many pions come out, how many protons come out, how many kaons come out. That's an observable which is called the multiplicities. And so various models, including CGC, can make predictions for what are the final multiplicity of particles that we observe. We can make a more fine-grained measurement of the particles by also binning them in momentum. For example, I can ask how many pions have momentum between 500 MeV and 1 GeV. And I count that. And then I ask the next question, how many have a momentum between 1 GeV and 1.5 GeV? And I can count that. And then I can make a plot of, the number of particles versus transverse momentum. And that's something called the particle spectra. And the particle spectra themselves provide information about the degree to which the quark-gluon plasma has thermalized. If the thing had perfectly thermalized, the prediction from the model would be that you should get thermal spectra for all particle species with the mass in this thermal distribution function set by the mass of the particle that you're looking at. So for the pions or the protons or the kaons. If it's not perfectly thermalized, then there's some information also about the non-equilibrium corrections that are hiding in the particle spectra. And you can use the particle spectra that are observed experimentally to peel out information about things like the temperature and also, believe it or not, the shear viscosity of the quark-gluon plasma. The second key observable that people have focused on in the last 20 years is something called collective flow. I know that you had some talks about this because I looked at the previous slides in your presentation. I'm not going to focus on this today. The collective flow is essentially emerges from the fact that in a generic heavy ion collision, they do not collide in a head-on, but instead they collide with what's called a finite impact parameter. So the center of the nucleus going to the left is different than the center of the nucleus going to the right. And if I were to look at this in the other plane, so rotate this entire diagram by 90 degrees, so I was looking down the beamline, I would see that the overlap region between those two nuclei is not circular, but elliptically deformed. And because of this elliptical deformation, there's going to be a higher pressure gradient along the short side of the ellipse than along the long side of the ellipse. And that pressure gradient will be translated into flow of particles more along the short side than along the long side. And you can experimentally measure this anisotropic flow, how much more is it flowing along the short side than the long side, and that's called the collective flow of the matter. Now, there's not just elliptic flow, there's also radial flow, which is hiding inside of there in a perfectly central collision. That's this transverse expansion that we saw earlier. And there's also higher order flows due to the fact that the two nuclei are not smooth pancakes, but instead lumpy pancakes. And by analyzing this observable, you can extract important quantities for the quark-gluon plasma, such as the shear viscosity to entropy density ratio, or even the bulk viscosity. So this allows you access to the transport coefficients, and by combining the first two, actually you can fairly well constrain the transport coefficients of the quark-gluon plasma. Another key observable in quark-gluon plasma physics is what's called jet quenching, and that I think you also had a talk about jet energy loss, at least fully coherent energy loss by Francois Arlio in this series. And the basic physics there is that I collide two nuclei, I might generate a jet, a high energy jet of particles. Normally that's a back-to-back jet with one particle zooming out this way and another zooming out that way. But if I generate a jet near the edge of this quark-gluon plasma, what I will find is that the one that escapes from the surface, well, it's basically unmodified by the plasma. The one that goes the other way through the quark-gluon plasma is going to get eaten by the plasma. And so there I would expect a sort of anisotropic jet quenching to emerge due to the production of the quark-gluon plasma, and that's called jet quenching. And it provides information about the momentum diffusion of high energy particles and energy loss of partons in the quark-gluon plasma. I'll skip the next one because that's what I'm going to focus on in the remaining slides, and go to here. This is electromagnetic radiation. Electromagnetic radiation, it at all times during the quark-gluon plasma evolution, it's also the particles have electric charge, so they're interacting electromagnetically. and you can produce photons at any moment, right, in time. You're going to produce really high energy photons in the first moments after the collision, because that's when the temperatures of that plasma are the hottest. And the great thing about photons is they're not strongly interacting particles, so they will escape basically unaffected and provide a sort of history of the thermal evolution of the quark-gluon plasma, and in addition can provide information about non-equilibrium corrections, not just the temperature itself. And then finally, if you were interested in measuring what is the size of the quark-gluon plasma that you generated, you can look at multi-particle correlations. So like a pi plus, pi minus correlations. And then by looking at the correlation functions, you can extract using HBT and interferometry the size of the quark-gluon plasma. So those are, at least by my estimation, the most important ones. There's others, of course, and everything has details piled upon details. What I'm going to focus on here today and in the next seminar is the suppression of heavy quarkonium. And it provides information about the screening of the color interactions between particles and information about bound state survival in the quark-gluon plasma. And in these two seminars, I'm going to focus on a particular heavy quarkonium, which is called bottomonium. And it is a combination of a bottom quark and an anti-bottom quark. Bottom quark has a mass on the order of, let's say, 5 GeV. This whole state has a mass on the order of 10 GeV. So by most people's standards, this is pretty heavy particle. You can look up its properties in the PDG. You'll find that it has a mass on the order of this 10 GeV scale that I said before. It has a very small width, so it's well identified and was discovered originally in the mid 70s and in normal high energy particle collisions. Another important fact about the bottomonium state, it has a rather large binding energy. And what that means in practice is it takes a lot of energy to break it up. So the rough estimate that you can make, just the ballpark for when will a state actually melt, is when the temperature is on the order of the binding energy. So the binding energy of the pion is like its mass. It's all binding energy. So when the temperature becomes on the order of the pion mass, that's when the pion dissociates. The higher the binding energy of the state, the higher the temperature has to be for it to dissociate. Now, if you calculate this in practice, what you'll find is that this number is really actually on the order of like 650 MeV. But we're physicists, so we understand what the tilde here means. So how we detect the upsilon 1s, in this case, this is the ground state of a b-bbar pair. It is detected through the decay. Of course, a bottom quark and an anti-bottom quark will eventually meet up with one another and they'll decay, and then they become a photon, and then that virtual photon will decay into muon pairs or electron pairs or tau pairs. And what the experimentalists do, not me, I'm a theorist, what they do is they just measure muons, and then they reconstruct their invariant mass, and they make a plot of the collected dimuon spectra, and then, as you'll see in a couple of slides, you find some peaks on top of that spectrum, and that's how you discover this particle. Yeah, I think that's everything. So we know a lot about bottomonium. Oh, the one thing, why did I go back? Oh, you might also ask at this point, why not toponium? Because it's even heavier, right? So top quark has an even higher mass. Well, it turns out toponium's not stable. Like if you look at toponium, the top quark will undergo a weak decay down to a bottom faster than the time it takes, the top and the anti-top to circle around with one another. So this is the highest mass beast that you can generate. We know a lot about bottomonium. It has a very rich spectrum. This was the state that I showed you on the previous slide, the upsilon 1s. It has these quantum numbers. There's also a thing called the eta B, which is the pseudoscalar. It does not decay into dimuons, so it has different decay channels, so it's harder to detect. So that's why the focus is typically on this state. Sorry, let me turn this off and dismiss. Good. It's reminding me that I have to do this administrative thing. All right, so the nice thing about these heavy quark bound states is that their spectrum looks a lot like a hydrogen atom, right? So we can these are all the S wave states, these are P wave states, these are the 2p states, and in fact you can just sit down, and I think I have a slide coming, and just do a non-relativistic quantum mechanics calculation with a given potential and predict very precisely what these energy levels are. Now, these states that are hiding up here, these are above threshold, so they're not really bound states, but they're indicated here. Now, you might ask, why focus on bottomonium? Well, as physicists, we always like to have some small parameter that we're going to expand in. In this case, the small parameter is lambda QCD over the mass of the quark that you're interested in. Lambda QCD on the order of 300 MeV, and in this case, the mass of the quark of 5 GeV. So that's our small parameter that we're going to expand. And the smaller that parameter is, the better. Now, in heavy ion collisions, there's a lot of measurements related to the J psi, which is a bound state of a charm and an anti-charm quark. The charm quark mass is about 1.3 GeV, so that number is not quite as small as for bottomonium. So that's why in the last decade, we started looking intensively at bottomonium, because everything's under better theoretical control in this sector. Now, you can ask the follow-up question, why didn't they do that to begin with? And that's because at SPS energies, and also to some extent at RIC energies, it's very hard to generate bottomonium. You need a lot of collision energy to generate a bottomonium state. So the production cross-sections are very small, so people focused on J psi. But with the advent of LHC, this became the thing to look at. You start generating them, I wouldn't say copiously, but enough that you can make measurements of them. The other reason that you want to focus on bottomonium states is because there are some competing effects that we might want to worry about. So the effect that we're looking for is that a bottomonium bound state flying through the quark-gluon plasma is going to break up due to its interactions with the plasma. And that's called quarkonium suppression in general. But there can also be modifications of quarkonium production from just nuclear PDF effects. So the fact that the PDFs in nuclei are different than they are in protons, that can change the production of bottomonium. As you learned in Arlio's talk, there can also be modifications due to the fact that my high energy quarkonium state propagating through the nucleus in these first moments after the collision, that can also cause them to lose some energy and result in a modification of their spectrum as well. But as Francois demonstrated in his talk, as you go to bottomonium, for example, this energy loss effect at central rapidities becomes a 5% effect. So it's under control. You still need to compute it in order to make quantitative assessments of what you've observed, but it's not a dominant effect any longer. And these NPDF effects can also be quantified. So this is all well and good. Whereas for the J psi, energy loss is bigger, the NPDF effects are bigger, so you have a lot more ingredients that have to be included in order to describe the data. Good. The other reason that you want to focus on bottomonium, this is also true for charmonium, but it's even more so true for bottomonium. You're only going to produce the bottomonium states in the first few fractions of a Fermi over C after the nuclear pass-through. And there's absolutely no chance that you're going to generate a b-bbar pair at a later time. I shouldn't say absolutely no chance. It's an e to the -10 chance. So you're going to get all of these guys are dominated by initial hard scatterings, and we can then compute exactly, you know, how many on average bottomonium states are we starting with? What is their momentum distribution? This is something we can calculate. And then we just have to take this probe and shoot it through the quark-gluon plasma. The other benefit of bottom quarks is that they're relatively rare compared to c-c-bar pairs. At LHC energies, you actually generate a fair number of c-c-bar pairs, and there's a probability pairs and also free chart, so both a J-psi and free C's and C-bars. And there's probability that these things can meet up and start reforming J-psi states. This is called recombination or regeneration in general. So, but with the bottom quark, you're lucky if you get one, maybe two per heavy ion collision event, bound state, and then you only have a handful of unbound b-bars flying around. So the probability of this regeneration is much, much smaller. So all these things taken together mean that modeling of bottomonium in heavy ion collisions is much simpler than modeling of J-psi. There's fewer ingredients, there's fewer knobs that you can play with, and therefore it makes the analysis more clean. So let me check the time again. All right, so I'll try to finish in a couple of slides, which means that I won't get all the way through where I wanted to get to today, but that's fine. We can push it to seminar number 2. So as I said on the previous slide, we're relying on the largeness of the heavy quark mass. In the large heavy quark, within the large mass limit, you can take any relativistic Lagrangian and then reduce it to a non-relativistic theory. And that's what's shown in this bottom equation down here is the Hamiltonian that emerges in the large quark mass limit. I have some potential-like interactions in this particular Lagrangian. I have a Coulomb plus some string tension, so there's a kind of Cornell potential hiding here. I have spin orbit interactions. I have Thomas precession. It all falls out of just doing, you know, all the systematic expansion of this heavy quark effective theory. And as I said, it works quite well. So this is just a model that with a student from roughly a decade ago, and what's shown here are the masses of these various states going from this pseudoscalar A to B, the upsilon 1s. These are their experimentally measured masses. We just take this non-relativistic Hamiltonian, solve the Schrodinger equation, and then you can reproduce the spectrum of all of these guys to, you know, a remarkable precision. So because of this large binding energy, I have to correct this earlier cartoon that I showed you. Not all of the hadrons melt immediately. So you're going to have some of these b-bbar states, bound states that survive up to temperatures on the order of 650 MeV. And then they have to propagate through the quark-gluon plasma. And as they propagate through the quark-gluon plasma, there's a chance that they get broken up through their interactions with the quark-gluon plasma. So now we can, in the last few slides, turn to the experimental observables. So we expect these states to be suppressed relative to their production in p-bar because of this quark-gluon plasma effect primarily. And that's for 2 reasons. One, there is weaker binding between the states due to the fact that there's Debye screening of the strong interaction. That was the original motivation for, you know, studying J-psi suppression going back to the 1980s. But what we've learned in the last decade is that there is this Debye screening effect, which corresponds to a modification of the real part of the heavy quark potential. There's also an induced imaginary part to the heavy quark potential, and this imaginary part maps directly to the sort of in-medium spectral width of the states. So, and this just is just the fact that in addition to this screening, there's also stuff slamming into you all the time, and that results in a larger spectral width. So the screening effect you can see directly by looking at a proxy for the potential, in this case, the singlet free energy between a heavy quark and an antiquark, and you can see the modification. The black is 0 temperature, and going down here is increasing the temperature little bit by little bit. The bottom left thing shows actual experimental observables in a PP collision. So these are the peaks that I was telling you about. This is the dimuon invariant mass. We see a 1s peak, a 2s peak, and a 3s peak. This is from LECB. And then the right is showing you what we would expect this picture if I could generate a quark-gluon plasma and hold it here in the room with us at 330 MeV and measure that spectral function. You would see that it's much broader than this, and that's due to these medium interactions of the b-bbar state with the quark-gluon plasma. And if I kept increasing the temperature, they get broader, and even the 3s now you can barely even see that it's even a state at all, and the 2s as well. It's completely gone. I keep increasing the temperature, and then eventually they're all gone. Now, of course, the quark-gluon plasma is complicated. I have to integrate over some temporal history, which means the temperature is changing and all that. I'll tell you how that's done in practice in the next, in part 2 of the seminar. The observable that we get in the end is by the following analysis, right? So the left shows you what you would get in a PP collision. This is now normalized to that background. So they've subtracted off this little curve that's going here to make it look flat. You can see from CMS, it is designed to detect these states. It has a lot of points there. So the resolution is super high. You can really do a great job with CMS, and you can very clearly pick out in a PP collision the 1s, the 2s, and the 3s. So if you do the same analysis in a lead-lead collision, this is again as a function of the dimuon invariant mass. What you see is the 3s is gone. The 2s, there's barely a peak there at all. There is a peak that looks like the 1s, but then it becomes a quantitative question of is it as many as we would expect? So the control in this case is that I imagine that my lead-lead nucleus is just a bunch of PP collisions. And I just scale up the PP cross sections for production of these things by the number of binary collisions that I expect between nucleons in my 2 nuclei. That is this red dashed curve, which I've called PP scaled here. And so this is what you would expect if no quark-gluon plasma or interesting physics occurred, and this is what you get. So you can see that the 3s is gone, the 2s is almost completely gone, and there's even suppression of the ground state itself. So that brings me to my conclusion slide. In the second part, we'll go through how do you quantitatively understand this based on starting from the QCD Lagrangian. The conclusions for today are the sort of overarching ones that, well, we can do this now. When I started my PhD in roughly 1994, 30 years ago, this was all speculation. There were no experiments generating the quark-gluon plasma. Now we have lots of experiments and lots of data on the quark-gluon plasma. These experiments allow us to study non-abelian many body physics, non-abelian because QCD is involved and it has non-computing generators for the gauge group. We have now, after that intervening 30 years, we have a fairly good understanding of the equation of state, both from numerical lattice QCD calculations and also from these high temperature QCD resummations. At low temperatures, we have a good understanding in terms of the hadron resonance gas. So in the next part, which will have to tell me when I'm supposed to do that, I am going to focus on the suppression of heavy bottomonium. And my claim, as you read in the abstract, is it provides a smoking gun for the creation of the quark-gluon plasma. We see that in central collisions, you get a suppression factor of roughly 1/5, and there's no way you can do that with purely hadronic interactions. It has to be a quark-gluon plasma. So it's one of these observables where it's black or white. There's no gray area. All right, with that, I'll finish. Thank you.
Taking a long time to get to a point where you really have something that's it. No other interpretation available. Right? I mean, you remember the case for quark-gluon plasma at the SPS ages ago.
Yes.
That science got into trouble over because this was a combination of a gazillion things.
Yeah. For the students in the room, so they tried to announce the discovery of the quark-gluon plasma at SPS energies in the 90s based on the suppression of J psi. But people got into a huge fight because there were these competing NPDF and cold nuclear matter effects that could give you a suppression on the same order as what was observed in the experiment. Eventually, they decided that it wasn't clear enough and they didn't make the announcement. So it was Rick that did make the announcement officially, not based on J psi suppression. No, you're going to correct me, Will?
Yeah, point me to the announcement from Rick.
Well, there's no official announcement, right? I mean, we've just sort of come to accept it as a community. And I don't know, I can point you at various press releases from Brookhaven National Lab where that say, you know, Rick creates the quark-gluon plasma. You're looking for a white paper.
Strongly coupled fluid, nearly ideal fluid is what they said.
Yeah, well, that's mincing words.
It's a fun history.
Do we have questions? Young guys first. All right.
Yeah. At one point early on in the talk, I kind of struggled to understand. You mentioned the gluon cloud. It was around slide 5. Sorry, I know you just told the thing.
Here, yeah.
You're not sharing your screen right now.
Oh, sorry. Let me share the screen again. And let me just try to share just the PowerPoint. Do you see it now?
Yes.
Good.
Can you just explain that again? I didn't quite follow how that whole mass of the gluon comes about.
Yeah. So the mass, you would even get this. So this is for quarks in this plot, but you would even get a sort of mass for the gluon out of this. But let's focus on the quarks for the time being. So when I have to propagate a quark through along, it's of course can radiate gluons off, right? There's virtual gluons popping off of it at all times, and then it's reabsorbing these gluons. So there's this kind of sea of gluons that it's propagating through, even in vacuum physics. And that sea of gluons affects the moment of inertia of the quark, and we interpret this as the mass. Now, the way that this calculation is done is they solve for what's called the self-energy of the quark as it's propagating along. The first diagram in this self-energy expansion is the one where you have a quark, it emits a gluon, and then it reabsorbs that gluon at a later time. And then you can solve this self-consistently to get the full propagator, and that's what's done to get these lines that are going through here. So the gluon cloud is the gluons that are always the virtual gluons that are always being radiated and reabsorbed by the quarks as they're propagating along.
Okay, yeah, that makes sense. Thanks.
Yeah.
More question. Yeah. For the observables for the QGP, you mentioned that you use jets as probes. I was wondering, there was a good slide you had with the space-time diagram of QGP.
Yeah.
Is there a specific place where you expect lots of jets? Yeah, this one, where you expect lots of jets to be forming? Would it be very early and then?
Yeah. The jets are formed very, very early. So if you can just look at their momentum. So if it's a jet with momentum higher than 10 GeV, it's in this region, right? For sure.
Right. I was just curious. So you also mentioned then that you would compare that to a jet that formed sort of on the exterior of the plasma. Would that just be
Right.
spatially?
Well,
or...
yeah, that's just spatially, yeah. So
Okay.
yeah, that's just spatially. So in this diagram, which I wish I could make it stop moving at this moment in time. Yeah, so you'll still get a very high energy jet that's produced at very early times, but it might be produced here and fly out, you know, on this side and fly through on the other way. So that's just has to do with the spatial distribution of their initial production points. Yeah.
Okay.
Okay, great. You'll have time to think of more questions because I'm coming back
I've got a question. So what do you expect the effect of increasing baryon chemical potential will be on this bottomonia?
On quark-gluon plasma in general or on bottomonium?
On bottomonia.
Yeah, so the first thing is that well, if you just go back to this sort of Matsui-Satz picture, the reason that you get screening is because the gluon acquires a finite temperature mass. It's called the Debye mass. The Debye mass depends on the temperature squared, but also on the baryochemical potential squared. So as you go out into the diagram, it's not like it turns off. It just transmutes into a different form of screening that has to do now with the finite baryochemical potential. So you can make predictions just based on the kind of old screening models of what would happen at finite baryochemical potential, and you get a very similar picture that it will dissociate. Now the problem for bottomonium at finite baryochemical potential is that you're lowering the beam energy. And the moment you lower the beam energy, you turn off the production cross sections for these things and you're not able to see them.
But Mike, isn't a big
Yeah.
part of your work showing that the sort of naive screening picture of Matsui and Satz is actually far
Right. Yeah.
from
So
complete?
I don't know the full answer because nobody, and you know, somebody should do it. The full analysis at finite T and mu B, it should be done. The reason I give the warning is that, you know, you can do it, but will it ever be observed? Nobody can measure it. So you might be just wasting your time. Now, we've had talks with the Munich collaboration about doing this, so I don't want to discourage people. You know, it's something we talk about, but then we also talk about the fact that, well, you know, will we all have data to compare to? I don't know. I doubt it. Now, you can do it for the J psi. There you might have some hope.
Okay, so I guess I have another question. So earlier on, you mentioned that you'd be interested in studying the phase diagram of the finite mu b. Yeah, I just want to find out how, you know, what are you looking at? Are you looking at those low energy collisions then to do that, or?
Yeah, so the way you study this region is the low energy collision. So in very, very low energy nuclear collisions, actually the nuclei don't pass through one another. Actually, at super low energies, they can actually combine. And you can generate something that has, say, twice the density of a normal nucleus for some amount of time, right? And they can even bounce off of one another, and you create a region of very high compression where the number of quarks per Fermi cubed is super high. So that's done by low energy nuclear collisions. Yeah.
Okay. So I was just wondering if well, where you're going with this? Well, I guess talk next week. Will you be trying to talk about how you study this still, or?
Well, I'm not going to talk about this part of the phase diagram. The second part of the talk is just continuation about bottomonium and how you actually calculate its suppression and then I'll show you a bunch of data with theory curves going through it.
Oh, okay.
Yeah. The second part is all bottomonium.
Oh, okay.
Maybe to briefly follow up on the previous question, or the previous question about high boron density and bottomonium.
Yeah.
How much oomph can you get out of going up to high rapidity?
Yeah, so the bottomonium production cross sections also drop off with rapidity. It's like a 1 over a cosh. So if you go to like rapidity 5, you also start turning off the bottomonium production. Of course, with a fixed PT and a very high rapidity, you know, that guy has a higher energy than another one. We model the full 3D evolution now, so we include the rapidity dependence of all of this in the simulations. So that's done.
Okay.
You know.
I guess we'll have to wait for the next talk to understand a little better how this is going.
Yeah. Well, I have to average. You know, if I told you the whole story in the first talk, you wouldn't show for the second one.
We wouldn't be listening.
So,
yeah, absolutely.
Yeah, exactly. This is how you make a successful sequel.
Yeah, I'm just curious. Just one more question. So I'm curious then. Do you have any idea how these lower energy collisions, how the initial state is treated? You no longer can argue for color glass condensate, I imagine, right?
Yeah, so you don't have color glass condensate, although people can take that and extrapolate it down and try to make models based upon it. Most of the low energy collision models are just assume kind of Monte Carlo Glauber kind of models where you have some nucleon positions that you're sampling. Yeah, so there are people that try to apply CGC down at even lower energies. So music, kind of IP plasma kind of initial conditions, but the lower in the energy goes, you know, the more suspect it becomes. But you don't have much modeling to rely on. So I mean, you don't have any you don't have no first principles to rely on. So it becomes a modeling. That's what I meant to say. Sorry.
Okay, and lastly, like if I'm getting what what you're doing here, are you then hoping to use this bottomonia as like kind of a thermometer?
Sorry, I didn't understand the question completely.
Are you hoping to use these I guess the suppression some thermometer like you know, to measure what's happening with the temperature of this problem level?
Yeah, so the first thing that you can do with bottomonium is measure the temperature, right? So that was the original, well, or with quark-gluon in general, is that by, you know, that was this that I didn't discuss on this slide, because the melting temperature is different for these different states. By looking at different states and their relative suppression, you can have another measurement of the temperature. Now, these days, I think we have a much better way to measure the temperature, and that's by fitting lots of hydrodynamic simulations to the spectra and such. So I think we can pin down the initial temperature much better there. Now the focus is shifted more on trying to understand the fundamental physics of transport of these bound states in the quark-gluon plasma. And there's lots of non-trivial physics hiding there. So I'll talk about that in the next talk.
All right.
All right.
All questions done. So let's say thank you again for a very thorough view of the topic.
Okay. Thanks, everyone, and I'll see you soon, I think.
Hope you still get some breakfast.
Yeah, we'll find out. Okay.
All right.
Thanks so much, Mike. Really appreciate it. Take care.
Bye.
Bye.